Hello and welcome to our new webinar, this time on software protection, safeguarding code against reverse engineering. A few words about me. So I'm Tim, I'm the chief scientist and head of engineering and one of the co-founders of Emproof. We are a startup located in the Netherlands where we focus on embedded reverse engineering. Where we focus on embedded reverse engineering, anti-reverse engineering techniques, such as software protection, such that firmware cannot be analyzed by third parties. So we are basically focused on advanced embedded security solutions. I own a PhD in binary program analysis and reverse engineering, and besides, I give trainings and lectures at industry conferences and universities. The goal of today is to discuss to do a small recap of common reverse engineering threats. Then we will switch into software protection, what it means to protect software against reverse engineering and how this can be done. We will combine this with a small demonstration. We will combine this with a small demonstration, and in the end, you will get everything that you can play around with on your own. So, if you are new to this series, there's already two webinars we did in the past. One is reverse engineering, how attackers uncover secrets and binaries, where we did a small introduction into reverse engineering and how it went. And then in the second webinar, Secrets Unveiled, what attackers find in embedded systems, we talked about taking a closer look at embedded firmware and digging into that, how we can find credentials there. If you are interested in these recordings or also get the slides and binaries, we can check it out. So you can go, for instance, to this website, and there you will find our past two webinars with the slides and so on attached here. And also this webinar will be listed later on here in this overview. Okay. That said, let's do a small recap about reverse engineering threats, and then we jump into software protection, our main focus for today. Reverse engineering, the goal basically from an attacker is to get a binary, like an embedded firmware for instance, and reverse engineer it, so analyze the binary code with the goal to extract secrets from it. And this can be used, for instance, to find bugs and do sabotage. It can be used to understand what's going on and to unlock secrets in the firmware, like understanding the code, for instance, what a competitor does, and copy this IP into your own product. And also, in terms of user, there is something like piracy, the interest in copy and removing copy protections and bypassing authentication checks and just unlock features, for instance, that the user otherwise has to pay for. So in other words, a financial gain in many different ways can be the attacker scenario. So what can we typically find in such binaries? We can typically find something like, first, hard-coded secrets, like cryptographic keys, serial numbers, passwords, and so on, network addresses, but also we can find more sensitive data, like secret algorithms that have been developed after years of research, or machine learning models, and so on. So basically everything which can be considered as private and that companies don't want to have shared easily with other participants. So we typically, in assembly on reverse engineering, start with something which is called machine code. This machine code is basically a sequence of bytes which is interpreted by the CPU as code. So the CPU, like the device of your computer or of your smartphone, works with instruction sequences, with byte sequences like that, and performs computations based on that. For instance, it might know that there is some encoding or decoding form, and then for this byte sequence, and then it might translate it to something like add R1 and a constant. So this would basically mean here we perform an addition with a register R1 and a constant, and here we perform a multiplication with R2 and another constant. So this machine code would be decoded by the CPU into assembly code and then executed. So, and this code basically represents high-level code. So we have a tool in reverse engineering which is called a disassembler, which can decode instruction sequences into human-readable assembly code. And based on that, a reverse engineer can analyze the code and reconstruct the high-level code, or even better, the reverse engineer can take a decompiler, which then takes assembly code as input and reconstructs the high-level code like the C code. And then we can, for instance, decode instruction sequence like this one into high-level C code like this one, where we just then have a calculate, a function name, which takes two parameters, param1 and param2, and then, for instance, returns param2 plus param1 multiplied by 4. There are open source reverse engineering frameworks in the wild that can be easily downloaded, that, for instance, allow you to load a binary, then inspect in the middle the assembly code here, and on the right hand side, you can see the decompiler output. And then you can get a better understanding of what the code is doing. And this can be done by everybody who just has some interest in reverse engineering. The person can then go, for instance, to the website of Ghidra, download it, install it, and then analyze an arbitrary binary. If you want to learn more about that, I would recommend you looking up one of our previous webinars where we talked about that. Otherwise, there are also lots of contents for free on the internet. So now we want to focus on, given that as a basic knowledge, how can we protect against that? Or is there any method like that enables us to prevent reverse engineering or to make it at least more complicated? And the answer is yes, there exists something like that, and this term is called software protection. Software protection has the goal to complicate reverse engineering attempts. Complicating means that we want to raise the bar for attackers to spend significantly more time on the same code, with the goal that it's harder to reverse engineer. So it's not impossible, because there is in reverse engineering, there is nothing like this cannot be reverse engineered, or this cannot be protected in a way that it can't be reverse engineered. But you can significantly raise the bar in terms of that the attacker has first to have significantly more knowledge about what he or she is doing and how to proceed. And at the same time, you can raise the bar that even if you have an expert level attacker, the analysis effort is significantly higher, and therefore the time is significantly higher. So in short, you basically increase the difficulty to do that, and you increase the time window to do that. And with that, you increase the financial gain a lot. So you make it significantly more expensive to reverse engineer a piece of software. Okay, now the question is, how can we do that? And well, if we talk about software protection, we have to take a look on how attackers really analyze code. And we already did it before. We have our tools like disassemblers and decompilers, where we open in a binary and then we can take a closer look at that. So let's just start with that as a small demonstration. Let's assume we have a small sample like Fibonacci. This Fibonacci code, just to show to you, this Fibonacci code is just a small function which takes in an variable n, and then it performs some computations like a equals 0, b equals 1, then we have s equals b, and then we check if n is equal to 0. If so, we return 0. Otherwise, we go into the loop and compute the nth Fibonacci number. And if we just proceed it like that, we can, for instance, open a terminal. Then we compile it like gcc -o Fibonacci.c and put it into a binary called Fibonacci. And then we can call the Fibonacci and just see that it computes this Fibonacci. Like for the first value, we get 1. If we take the fifth value, we get a 5. If we take a sixth value, we get an 8, and then a 9, and so on and so on. So this binary computes a Fibonacci sequence. We can also take a look at that in a reverse engineering tool like this time Binary Ninja. For that, we open Binary Ninja down here. And after it has been loaded, we, for instance, just open the binary there. So here we have our Fibonacci sequence. Let me recompile it again. So we have our Fibonacci sequence, and I can now put it in here. And then I can see down in the middle here that we have the main function, which takes some arguments, and then it prints a string fib result, and then it calls a function fib. And if we take a look into this function, we see that it basically gets an argument arg1. I can make this more beautiful, the output, by just limiting it to the current function. So like that. And now we, for instance, see we have this function fib here. Then we initialize some variables and we check if it's equal to 0, then we return 0. Otherwise, we have to do a loop and we compute something. So we can rename this, for instance, to the variable n, and we can for instance, rename to the variable result, and then it looks like that. So this is how reverse engineering would work. And now we work basically with something like a control flow graph that allows us to showcase, to see how the states of the code look like and how to go from one state to the other state. And we also can look at the decompiler, which basically gives us a high-level view of the binary. And now the goal of software protection is basically to make this code harder to analyze. And for this, we have active and passive methods. And let us first talk about the passive methods. The passive protections are called code obfuscation and data encoding. The idea behind code obfuscation and data encoding is that you basically leave the code as it is, function-wise, but you make it significantly harder to analyze because you add complexity to that. So for instance, instead of having a small graph and a small function with easy to observe control flow, you could build graphs like that, which add a lot of complexity and make it very hard to understand and see what's really going on in the function. So you basically can increase the complexity to impede reverse engineering. And you can also arithmetically hide keys and credentials, like in an encrypted or encoded format, and then decode it at runtime, such that if you have a decoding algorithm that looks like that, understanding the measures, what's really going on there, and seeing the data that you want to unprotect is significantly harder. So, and to do this passive countermeasure, this passive protection, the goal is basically to make it more complicated on the control flow level, but also on the compiler level. And while obfuscation can be significantly complex, I would like to showcase it to you on a very small example. So let's go back to our Fibonacci code. And this was the Fibonacci code we just saw before, where we can see that this looks like that, and then we see that we do have a loop, and then we perform some computations inside the loop. So if we take a look at code like that in the decompiler, we just saw it before, some minutes before, it looks very similar. So like here, it looks very similar. However, now we want to go one step further and obfuscate the control flow, such that we are not able to see anymore if this is a state which is executed first, or if this state is executed first, or this one here. What we do for that is that we can encode control flow, that we can encode the control flow in some form of state machine, where we say the state is initialized with 0, and then we have an endless loop, and this endless loop dispatches, in a switch case, this state. So we now basically have a control flow, have a state machine which dispatches control flow. And we can see if state equals 0, we, for instance, perform the initialization computations we otherwise performed here in the beginning. And then we check if n equals 0, we update the state variable to be 3, otherwise to be 1. So in this way, we basically encode these things here in something that looks like that. And if we look at that from a control flow perspective, we can't easily see anymore if this state is taken the first time, if this state is taken the first time, or this or that. So assuming we don't know the source code, we can compile it on the binary level. So with that, I would just enable this function again, obfuscated 1, recompile it, like this, and first execute it. And the first thing you can see is that no matter what input we provide, they behave the same. So the obfuscation itself changes how the code looks like, but it doesn't change what it really computes. And now, if we take this code, open it again in the binary, like this, and we go to this function fib obfuscated 1, we now see that if we take a look at the graph, we don't easily see what's computed in which order. Instead, what we see is that we have one large entry block here, and then we have several basic blocks that are connected in a loop. Let me undo some things. That are connected in a loop and go back to this block. So like these states here, then after computation is done, go back here. These states here, then go back here. So if you compare this with the unobfuscated version, we can see that we first execute these parts, then we have a loop here, and at some time we go out here. We can see that without looking at the code much. However, in this example, we see that we have one large loop, and we don't really see which state is executed in which order. This is control flow obfuscation. If we take a look at the decompiler output, there again we see initially, top of here, we initialize the state variable, we can just call it state, and then we start dispatching the state and check if it's 3, then we return a variable, otherwise we break, and then we check if state is equal to 0, then we perform something and reset the state, and so on and so on. So the control flow, while the original basic block semantics preserve the same, like each block, each state still does what it should do. However, the control flow between these blocks is now not that easy to see and understand anymore. And this is a technique which is quite common in basic reverse engineering. However, we can still, if we take a look at the decompiler output, we can still see, oh, there are some basic computations, like this is an addition, there are a lot of assignments and so on. So it's a bit more challenging to analyze, but still doable. Question is, can we do it even better? Like, can we improve upon that? And the answer is yes. Until now, we basically had something which was called control flow obfuscation. There's another technique we can do. This is called arithmetic obfuscation. And the goal behind arithmetic obfuscation basically is to make simple arithmetic computations hard to analyze. Let me give you an example. If you see a function in C like that, where you see int foo with two parameters, int x, int y, and you return x plus y, and you think about what does this function do, you easily know, well, this function takes two inputs, x and y, and adds them together. So this function could be named sum or add or something like that. Because here it's easy to see that this is a computation. However, what about if I have a function foo with int x and int y, where you have something like x or y plus 2 times x and y. What does this compute now? Well, as it turns out, this computes exactly the same like this one. So these two formulas are equivalent. They just look different. However, for us reverse engineers, it's not easy to see that this is just the same as a computation as x plus y. However, in the end it is. No matter which input values we use for x and for y, it will always behave the same like x plus y. And this is called arithmetic obfuscation, where we basically hide simple assignments, simple arithmetic computations in large complex formulas. And going back to our Fibonacci case, the first thing we did is that we encoded the control flow with something like that, where we had the state machine. And now, in the second state, we want to improve upon that, such that we do not only encode the control flow, but also make these assignments significantly harder to read. So what we could do, for instance, would be, we could do it like that we take the exact same loop, but for each assignment that was just a simple assignment or a simple computation, we make it significantly harder by encoding the computations in arithmetic formulas. In this case, all assignments are based on this formula we just showcased here. So everything like that is just the same as x plus y. So for instance here we see that we add n and 5. So this would be the same as n plus 5. And then we subtract n, and then we subtract 5, computing 0. So this formula computes basically state equals 0. And if we take a look down here, we see basically we try to encode this one. Or let's go back to this one, where we have s equals a plus b. We will now encode it in a form like this one, where we have s equals a XOR b plus 2 times a and b. And the assignment where a should be equal to b, we can now encode as a equals a XOR b plus 2 times a and b. This one is a plus b. And then finally we subtract a, such that we basically compute a equals b. So this can be understood as a equals b, and so on. So it's the same technique applied to all others, but taking a look at that, this simple formula just applied all over the place, and the code is significantly harder to understand. On the binary level, if we compile it then, so let me compile it again with calling Fibonacci 2. Then we compile it. And then we put in some values there, like 1, like 10, like 200. And you see all of the 3 functions compute the same, no matter the input. However, if we analyze it in the binary, like this one, it still encodes the control flow of the function. So we have control flow obfuscation, but also we see that the individual basic blocks are significantly larger if you compare to the one before, where we have just smaller states. Now we have larger states. And if we now take a look at the decompiler, we see a lot of computations here. And now it's not that easy for us anymore to really understand what's going on here and how these things work. Now we not only have control flow obfuscation, but also we have arithmetic obfuscation, which makes in combination things significantly harder to understand. And at the same time, the rules we just applied were very, very basic. Now think about what we could do if we take strong obfuscation, thousands of different formulas like that, and combine it even with further significantly more complicated or sophisticated obfuscation transformations. What you can get and generate for code that is really hard to analyze. This here is just one of the easiest examples I can think of. And even that can be a pain to reverse engineer. So, coming back to our slides, we basically tackled that there is something like code obfuscation and data encoding, which are passive protections to impede reverse engineering. Passive protections, that basically means they are just there. And if you take a look at it, you don't see, you see like a maze of complicated things that you have to analyze on your own. However, there are also something which is called active protections. Active protections have the goal to be I see the questions. I will answer them later on. So, active protections at the same time are basically guards in code that are inserted in the code and active at runtime. And these guards take care of pinpointing the environment if something specifically changed and then go into an error state. And this can be used, for instance, to detect debuggers or to detect code modifications and so on. So, for instance, in the case of anti-debug, if you have the first thing you will do is you create a check like that, where you say, if debugger detected, I then do some action. And this action, for instance, might be terminating the program. So like if a debugger is present, like if somebody attached GDB or WinDebug or some other debugger to my application, and this function detects that, then we might terminate, because we know we are actively getting analyzed. So question is how we could detect a debugger, and well, the answer there is there are a lot of documented and undocumented methods. For instance, if we check something like anti-debug Linux, we will find several blog posts about various anti-debug techniques on Linux. And the same goes for Windows. For Windows, we'll find even more, like this great reference of various anti-debug techniques, or we can see that we have an entire website here of various anti-debug tricks. So there are a numerous way, there's a lot of different ways to detect a debugger, but they have all one thing in common. The idea of anti-debug is basically a debugger changes the environment, the execution environment, the execution env in specific ways. Like for instance, if I attach a debugger, my application behaves differently if it crashes or if it throws an interrupt or something like that. Or some special purpose registers on the CPU have different values. So there are a lot of different ways that the environment changes if a debugger is attached. And therefore, by looking specifically for these changes, we know, well, applications can know if they're getting debugged or not. And then they can perform some action, for instance, terminate themselves. So, and the same goes for checksumming. Checksumming, or also anti-tamper, the idea there is that you can compute checksums over code. So, for this, I have to go a few steps back. So, if we take a look at some code, like this one, we see that these are assembly instructions. And as we have discussed in the beginning, these assembly instructions are just nothing else than a sequence of bytes. Here we can see that we have a sequence of bytes that encode this assembly instruction. And over these assembly instructions, I can compute a cryptographic checksum. I can, for instance, walk over all these bytes in this function and put it into some cryptographic function, which, for instance, XORs all these values or performs an MD5 computation or whatsoever, and then gets a large constant as output. So we basically on anti-tamper, which basically gets an input. We have a crypto checksum, which takes as input byte sequence of code and then produces as output just a large constant. And this large constant basically encodes or is some indicator, some short representation of this code. And Now, an attacker could go and, for instance, change some of the codes. For instance, here, instead of doing control flow like that, an attacker could just modify this specific instruction to just return a value, for instance. We could just do a return here. And if I do that, the byte sequence of the code changes. And if the byte sequence of the code changes because somebody modified a jump or modified a function to return something different or just want to crack something, then this checksum is not valid anymore because it produces another constant. So this constant will not be the precomputed constant. And if I then have a check like if crypto checksum, if something like that is not equal to the large precomputed constant, if I have something like that, then I know somebody changed something in the code, and then I can just terminate, for instance. So, and the same goes for anti-debug, where I can do something like if detect debugger, and if this is the case, I could just do terminate. And otherwise, I go on with my normal behavior. So these are examples for active protections. Compared to code obfuscation, which is a purely passive technique, we have something like active protections, which pinpoints the environment and check if something is suspicious, like if a debugger is present or if some code changed in memory, and if so, we can do counteractors like terminating the program. Terminating the program is just one example. For instance, another technique would be we could delete the file system, we could just proceed as normal but introduce small errors to computations, or we could just send a message somewhere, or whatever. We could go to some kind of fail state. So this is a safe check that basically allows us to detect if somebody tries to analyze the program at runtime, and if so, we can do a failure state. This is the idea of anti-debug and anti-tamper. Typically, you have anti-debug and you have anti-tamper, and you have code obfuscation. And the question is, how do these things play together? Well, let's think about it. If I only have anti-debug and anti-tamper, I can't modify the binary, or I can't attach a debugger. However, I can still analyze the code and then detect something like that. For instance, maybe this call here just checks if this conditional jump here checks if a debugger is present or not. In case a debugger is present, it goes to a failure state, otherwise it goes to this state. Let's assume that. And if it is like that, what I could do is I could just go to patch and then do something like always branch or never branch, such that I basically patch out the anti-debugger check. Or I could patch out the anti-tamper check the same way. So therefore, it's not a good idea to put these things just as they are into the binary. Instead, you want to try to combine it with code obfuscation. So if you have obfuscated user code, and if you combine it with obfuscated anti-debug code and obfuscated anti-tamper code, in the end, you have just a lot of code which is obfuscated and you can't really analyze. And as an analyst, you have a hard time to decide if this is user code, if this is an anti-debug check, if it is an anti-tamper check, because everything is mixed together. And therefore, the takeaway is that good software protection combines obfuscation and anti-debug, anti-tamper, and mixes them. So basically, we don't have the one, we don't have the other. In the best case, we have both. Because then we can't only analyze it statically, but we can also analyze dynamically, and we have to analyze and bypass the obfuscation such that we can, or at least some layers of obfuscation, such that we can attach a debugger and so on. So this is how the idea of self-protection works. We have passive protections, we have runtime protections, and in combination, both of them are pretty strong. If you want to play around with that on your own, you not only have this samples and this recording and so on, but there's also an online demo of our in-house obfuscator, which you might be interested in taking a look at. Let me showcase that. So if you go to demo.emproof.com, you will find here the IP protection demo, and if you click on that, you get 3 windows. One window displays source code, then here we have the unprotected disassembled binary and then the protected assembled binary. So let's say we want to take some algorithm, like we take a base 64 encoding. Here we can then take a look at the source code of the base 64 encoding. And now we can compile it, in this case, for the RH64 Linux architecture. So we can compile it. It takes some seconds. And then here in the middle, we have various tools. The first thing is we can take a look at the disassembled code. This is now the ARM assembly code. However, we also can take a look at the decompiler output. Then it looks like that. Then we see significantly more, like it's not nice to read, but we can relate, like these things here one-to-one relate to these things here. So we see it's nearly the same. Or, sorry. Another thing we could do is we could show the CFG, and now we take a look at the control flow graph here like that. So this is something we want now to protect against reverse engineering. What we could do is we go down here, we, for instance, take a control flow obfuscation scheme and then say we protect it with Linux. Okay, since I reloaded, I have to redo the first step, but this will take only a while. So I compile it again. So, and now we can choose an obfuscation and obfuscate it. And after it's been processed, we can take a look how it behaves. So now, if we compare the original CFG control flow graph with the protected control flow graph, we already see here this one is significantly shorter because the decompiler and the disassembler, like the analysis tool in the background, doesn't know how to proceed. It just is able to only analyze fragments of the code. It doesn't see the other code at all. This is an indicator that there's some that the protection already works. We can take a look at the disassembler, and we see that the code does look different. However, the most difference we will see in the decompiler. If we take a look at the decompiler and we go to this function base46 encode, we see a lot of code here and see how it relates to this one on the left. However, if we now take a look here, we see that we call another function, and this another function cannot be really analyzed. Here, the decompiler just didn't know what to do and shows us everything the decompiler knows, which isn't that much. So in this case, the obfuscation has been successful. And if you want to play around with this online demo and get some explanations, there are also some great guidances, like the explainer which allows you to play around with first the things that go here, how this works, but you also have resources like IP protection, where you have a nice explainer on how it works, then how different obfuscation schemes work, and so on. So this is a great example and a great slide deck here to play around with that. This here, for instance, is control flow flattening. This is the control flow obfuscation. We just took a look at the Fibonacci code and also at in the demo here. So you get great explanations here. So if you want to play around with that, it's a great start. So coming back to the slides. Here's again the link for the online demo. And to conclude this webinar, that we talked about common reverse engineering threats that can be used for piracy, for competitor analysis, and so on. And then we have something like passive and active methods to prevent reverse engineering. Then you will have the online demo to play around with, and of this webinar today, the recording, the binaries, the samples, the slides, you will find later on here in this link. Now, you have time to ask some questions, like we have 15 minutes to answer some questions. If you are, so feel free to ask them and to check them. And in between, I will start at the top with the questions and answer them. So the first question is there any concern over using optimizations because I'm using optimization level 0? Yes. So in general, no. In this example, yes. So what I did here is I have this code and I put it with 0. The question is, what happens if we add a higher compiler level, like optimization level, like 03? If I do that, let me just showcase that. In this case, it will kill most of the obfuscation because this one is significantly too simple. So let me do that with 03 and compile that. Let me first show it behaves the same, still works the same. However, now if I close that and I open that again and I go to the protected sample, you see we still have control flow flattening and the code is still obfuscated, but it's not that much obfuscated anymore, so it looks a bit different. So in this case, it didn't make too much of a difference. At the same time, if I do only some basic things, the likelihood that the compiler can optimize it away is quite high. So therefore, good obfuscation is resilient against compiler optimizations, or let's say compiler optimizations even make obfuscated code even harder to analyze. But if I would just put something easier in here, so if I just would, for instance, do something like a plus b plus 1 minus 1 or something like that, this one the compiler would kill immediately. So yes, compiler optimizations do make a difference. Yeah, they do make a difference, especially if the examples are simple. So let's go to another question. Would you expect to see such level of obfuscation in embedded real-time systems where performance matters? Wouldn't be a trade-off for the developer? Well, yes and no. Obfuscation itself adds complexity. And as I have shown it on the slides, like here, complexity can get very complex and therefore the code can significantly get larger and slower. And this is something like that you see very often on desktop systems where size does not that much matter, where it doesn't really matter if your binary is 1 MB or 10 MB. So this usually is a lot of, is pretty common. However, on embedded, especially on real-time systems or small devices, you can't do something like that. What you usually do there is that you build sophisticated obfuscation methods that don't add too much complexity, but still are very hard to analyze. And there, especially this combination of active and passive methods, especially the combination done right, is the thing that adds the security there. Because you can't escalate in size too much. At the same time, you can combine passive and active protections in a smart way, such that the security level is comparable, but especially designed for small end devices. And then, also, what you don't want to do is you touch real-time systems, like real-time code. Especially if it must be cycle exact or something like that. What you usually do is there that you add maybe some code decryption stuff where the code itself is not really protected, is not really touched at runtime, but initially you add, during the boot up phase, you add some heavily obfuscated decoding phase, for instance, such that the original code is only available at runtime. Something like that would be also common to do on very small devices. And by the way, our company, Emproof, is basically specialized for doing embedded IP protection. We see us itself as our main focus in the embedded world. Then another question, does it target specific function or the entire binary? So also this is a pretty good question. The answer is always it depends. There's a possibility to add obfuscation to only specific functions or to only specific code parts. There's also the possibility to blacklist specific code parts, like to touch everything besides a specific set of functions. And there's also the possibility to protect everything. So, like a good obfuscator gives you a lot of freedom in terms of configuration. If you want to protect everything, only specific things, how you want to protect it, if you want to blacklist things, whitelist things, and so on. So this has to be done in an obfuscator. There's another question. In the IP protection demo, do you use indirect branching in addition to plane control flow flattening? Yes. So basically, indirect branching means that you compute the result of a jump at runtime. That you don't basically have something like jump, where is it, for instance, that you don't have a jump to a concrete address, like this one. But instead, you, for instance, patch it to jump to RDI, to some register. And this register then contains a computed value, and this value is computed at runtime. And this way, you can't really easily see where it goes. And yes, in the IP protection demo, we use a computed jump. We can see it here. We can see it here that here we branch to a register and it's not really clear where this register goes to. So yes. There's another question. No, there's no other question. So yeah, these were right now all questions. Are there any additional questions? There are two more questions. One is, while talking about embedded devices, FPGAs and other resource constraints devices, have you explored the problem for trying to add obfuscation for the CFG and arithmetic statements while optimizing the size of the final code for specific device constraints. Something like multi-objective function optimization problem. Do you know some resources topics for that? We played around with that, yes. And we came to some conclusions that it works in some cases, but we have to be very careful with that. And in general, there are not many resources out there. Some resources, this is often private IP of software protection companies, and therefore you don't find that much out there. So sorry about that. But optimizing CFG and arithmetic statements for code size and so on, this works for sure to some extent. There's another question. By obfuscating only part of the functions, will it make the obfuscated parts reverse engineer the other parts that are not obfuscated? That's always a good question. So yes, if you know that this is, for instance, a well-known implementation of something, and you recognize specific parts, let's say you recognize that there is a loop that adds two values and does some assignments, like this one. Let's say you recognize this part, and you recognize that this part looks like a partial Fibonacci computation. Then, of course, you can do an educated guess that also all other parts of the function might be heavily obfuscated. You might just say, hey, maybe this is a Fibonacci sequence because this part looks familiar, and then you can just do an educated guess and observe if it really behaves like a Fibonacci. So yeah, if there are some parts not obfuscated and you, for whatever reasons, recognize parts of that, then you can take this knowledge and do some educated guesses. Yes, good question. Other questions? Okay, then I think we call it a day. Thank you very much for your interest and for your questions. This webinar will then be published soon, and there's a link where we will find all the information. So thanks a lot for your questions and your attentions, and see you soon. Goodbye.